Before we can begin analyzing data or using it to train our learning algorithms, we need to clean it. This means we need a way to detect and correct errors in our data. While any given dataset can have many types of bad data, such as outliers or incorrect values, the type of bad data we encounter almost always is missing values. As we saw earlier, Pandas assigns the value nan, or not a number, to missing data. In this section, we will learn how to detect and deal with these nan values. In this data frame, we have 3 nan values, 1 in store 1 and 2 in store 3. However, in cases where we load very large datasets into a data frame, possibly with millions of items, the number of nan values isn't easily visualized like this. For these cases, we can use a combination of methods to count the number of nan values in our data. This combines the isNull and sum methods to count the number of nan values in our data frame. Let's break this down. The isNull method returns a data frame with a boolean for each value in the store items data frame, true when the value is none. In Pandas, logical true values have the numerical value 1, and logical false values have the numerical value 0. Therefore, we can count the number of nan values by counting the number of logical true values from this data frame. Using sum once gives us the number of nans in each column. We use sum again to get the total number of nans for the entire data frame. Instead of counting the number of nan values, we can also do the opposite and count the number of non-nan values with the count method. Now that we know how to find out if our dataset has any nan values, the next step is to decide what to do with them. In general, we have 2 options. We can either remove or replace missing values. To remove them, we can use the dropNA method. We can set the access parameter to 0 to eliminate any rows with nan values. We can also set access to 1 to eliminate any columns with nan values. The dropNA method drops these rows or columns out of place, meaning the original data frame is not modified. You can remove them in place by setting the keyword in place to true like this. Now, instead of eliminating nan values, let's replace them with actual values. As an example, we could choose to replace all nans with the value 0. The fillNA method can be used for this. We can also replace nans with values from the previous row or column with something called forward filling. This replaces each nan with the value from the previous value along the given axis. Here's the original data frame again. Notice that the 2 nan values in store 3 have been replaced with the previous values in their column. However, notice that the nan value in store 1 did not get replaced. That's because there are no previous values in this column, since nan is the first value in this column. However, if we do forward fill using the previous row values, this won't happen. We see that in this case, all the nan values have been replaced with the previous value in that row. Similarly, you can choose to replace the nans with the values that go after them in the data frame. This is known as backward filling. This replaces each nan with the next value in that column. The nan value in store 1 has been replaced by the next value in its column, but the 2 nan values in store 3 did not, since they are the last values in their columns. The fillNA method fills the nan values out of place, so set the parameter in place to true if you want to modify the original data frame. We can also choose to replace nans by using different interpolation methods. For example, this uses linear interpolation to replace nan values using the values along the column axis. The 2 nan values in store 3 have been replaced with linear interpolated values. However, nan value in store 1 did not get replaced since there is no data before it to allow the interpolation function to calculate a value. We can replace nan values with linear interpolation using row values like this. Like the other methods we saw, the interpolate method replaces nan values out of place.